bad boy. Okay, we're recording. So welcome to Fluid Mechanics today. Before we do anything else, I wanted to kind of, deal with a couple of, I don't know, little things that are kind of happening here. First of all, my phone number. Let me share a whiteboard real quick. Whiteboard. So this will be the last time you'll get my phone number. If you're doing that homework or you haven't started that homework yet, you should text me. You don't have to. You can just say you don't feel comfortable with it or you don't feel like it. So it's 510-479-6420. Again, if you don't feel like doing it, it's totally okay. Okay, but there it is. That's my phone number. Okay, so that's one thing I wanted to make sure that you guys had. Number two, some of you guys have texted me because the homework wasn't giving you, like the Connect version of the homework wasn't giving you your score. I think I fixed that. So if you want to go into Connect and you can actually like look at your score like while you're doing it, so you know if you need to redo it. Sorry about that. That was there's like a million buttons you have to click, little boxes and things when you're creating those things. I tend to screw it up. What's up?
I'm sorry, I was going to say I didn't hear anything you just said after you said your phone number because I lost connection.
Oh, okay. Well, you should be able to see your score on the Connect homework as you go now, instead of like getting to the end and being like, well, do I need to redo this? I don't even know. Okay. The last thing is, well, there's two more things. Okay. So a lot of you have had trouble with this particular problem, and it's actually for a good reason, because it really makes you think about the pounds mass issue. So there's a problem on Connect, and it looks something like, it's a capillary tube. And so it's like this, and there's some water in there, and we can make it blue because actually it's not water. It's in this case, it's mercury. Okay. And mercury and glass hate each other. So it looks something like that. Okay. And so what they did in the book is they said, okay, well, the density of mercury, this is what they told you. Hold on, give me a second. I do need this. The density of mercury is about 13.55 times the density of water. So hold on. So they said it's like 845. I don't know exactly what number they gave you, but it's something like this. 5.2. And they said this is pounds mass per cubic feet. Okay. As you guys know, especially from that huge note that I gave you, I mean, I think I even said it incorrectly in class, but here it is, so if we remember force equals mass times acceleration, we can always remember that a Newton, 1 Newton equals 1 kilogram times meters per second squared. Okay, that should already be in your head. And we should say that 1 pound, and that's a pound force, equals 1 slug times feet per second squared. Okay, so this is the unit of mass that works in your equation, because it's the one that if you combine it with this, it's going to give you pounds. Okay, if you have an equation and you plug in a pound mass, nothing's going to work out right. Okay, it's just going to it's going to be this huge, awful mess. So, so what do we do when we get a density that looks like this? Okay, what do we do with that? Okay, because if we plug this into our equations, like for example, let's suppose I wanted gamma. Okay, and this is going to be an error, so don't write it down if you, let's suppose I wanted gamma. Well, gamma equals rho times g. Okay, so if I'm like, okay, well, I got rho, 845.52 pounds mass per cubic feet. Okay, and I do that times g. Well, g is 32.2 feet per second squared. Okay, I'm going to get gamma equals, well, now I've got a problem. I would get some number, who cares what the number is? Okay, it would be, I could say it's a wrong number, but it's not necessarily a wrong number. It's just a sloppy number, because the units are per cubic foot on the bottom, but pounds mass per foot second squared does not give me pounds, which is what I want. We want slugs times foot per second squared. Okay, so this creates a problem. And this is kind of the problem that most of you guys who asked me, this is kind of what you ran up against. And it was good because this is why we do homework. It's so we can like think about things that otherwise, like, you know, we beat our heads against the wall. Maybe we even get a bad grade, but that's okay, right? It doesn't matter. The homework's 10% of your grade. It's so that when the exam comes, you've already thought about this. Okay. And in this case, you made the point to ask me the question. So enough of you asked. So I decided to like talk about it right now. So what's interesting about this is what you would do. This is actually really simple to fix in this system. This is the only place where a pound mass is actually kind of useful. But I'm not gonna do that bit of it right now. What I'm gonna do is I'm gonna show you how to convert. Just because more often than not, usually when you get a pound mass, you're gonna want to convert it. Okay, and so what we do here is we say, okay, well, 845.52 pounds mass per foot cubed. So this is a row. Okay, now we're going to convert that. This is that stoichiometry, and we'll say there's 32.2 pounds mass per slug. Okay, so if we do that, you know, with my calculator, 845.52 divided by 32.2, and I get 26 point. I always like to keep. I always require that we keep at least 5 significant digits all the way through the problem. And so we're left with slugs per cubic foot, okay, because these cancel. Okay, cubic feet. Okay, now we've got density. Now if we want gamma, I can do rho, density times gravity, and I can do 26.258 slugs per foot cubed. Okay. And now we're going to multiply that times gravity, which is 32.2 feet per second squared. Okay. And note that now slugs feet per second squared, that's a pound. So I get pounds per cubic foot. Okay. So that's gamma. That's the specific weight. So if we multiply by 32.2, we're going to get 845.52. Okay. So hence, only time that this is easy for you is this. Okay, if on Earth, then, right, and gamma is 845.52 pounds mass per cubic foot, then, excuse me, if rho is that, then gamma is 845.52 pounds force. For me, a pound is a pound per cubic foot. Okay, so it's very circular. It's very circular logic, but this is the exact reason why we have that dumb unit pound mass, and it screws up everything else, but it does make this one conversion easy. Okay, any questions on that? Okay.
No.
Go ahead. Okay. Was that a no? Okay. Anyway, so that's the idea behind that. Okay. The only other thing that I'm a little disappointed with this problem, and I don't blame you because of the way the problem is with this problem, is that what I wanted you to do is that what a lot of you did is you started from this. H equals, I can't even remember this formula, 2 gamma something rho, I don't know, right? There's a formula that we solve for in class. I can't remember what it is. And you guys just started from that, right? And what I want to be clear here is this is not a plug and chug class. I'm not asking to see if you can plug numbers into an equation. Okay, what I want you to be able to do is I want you to be able to go in and draw a free body diagram and solve for something else. So ideally, when you started this, you would have started with the free body diagram, because one of the most common questions, if you look at my old exams, now granted, one of the things that I'm pushing in this particular class is to try to get more variety on those. So you're going to look at the old exams and you're going to be like, oh, he always asked this question, and then I'm going to ask something different, and you're going to feel cheated. But I'm telling you right now, I'm going to add some variety. Now, to some extent, there's only so much I can do on this first test. So there will be similar questions. They'll never be the same. But like one common question that we ask, or like that a lot of fluid teachers ask, is they'll say, how high will the water rise in a capillary tube that is shaped like a prism. Okay, so now we've got water here, and let's draw the bottom of that thing. Okay, so if this were my capillary tube, how high, what is this? What is this height right here? Okay, now they won't normally say like, what's the equation, but you should be able to derive that equation based on what we did in class. And it would be, well, we would draw a free body diagram. Here's my fluid. Okay, the pressure on the bottom and the pressure on the top are the same. And then I would say, and I've got this, there's like the surface tension force is pulling up on these edges. Okay. And so we've got F sigma. Now there's a little angle there, theta, cosine theta. That's my upwards force. And my downwards force is the weight. Minus the weight equals 0. And what I'd be looking for here is, did you understand what I was doing when I did this, or did you just copy it all down? Okay, so the F sigma in this case, this would be sigma times the length of contact between the water and the glass or whatever this prism is made of, cosine theta minus the weight. The weight in fluid class is gamma times the volume equals 0. Okay, again, we're working vertically, so sigma, now this L expands. That's the length of contact between the water and the glass. So that would be this length right here, whatever the perimeter of that triangle is. So I'd have to give you variables for that, perimeter of triangle, okay, times the cosine of the angle, minus gamma times the volume. Well, what's the volume? It's a prismatic thing. So it would be the area of a cross section, 1/2 base times height, times this height. Right. So again, I'd have to give you, so this would be, 1/2 base times, you can't call it the height. So we already have H is already defined. Base times maybe capital H, and multiplied by lowercase h equals 0. Okay, and then you would rearrange and solve for it for lowercase h. And so, that's kind of what I want you to be able to do. Right. So, I want you to be able to think about, okay, in a capillary tube, what's going on? We've got these two forces balancing. What can we, can we derive? Can we figure this out? Because, let's face it, like as an engineer, you're going into some situation and you're looking at something and you're trying to figure it out. If they already have the equation and all they need to do is plug numbers into it, well, they might as well just ask a computer to do that. Right? They don't need you, for that. I don't want to say they can train a monkey to do that, but the computer can do that. Your job is to think. So that's what I'm asking you to do. Let's see. Okay, and then the last order of business before. Wait, any questions on this? Okay, the last order of business before we move on is make sure to give me those survey results. I haven't checked how many I got. I tried to get y'all to finish them last night. I'll check them this afternoon and see if I have enough. Some of you have texted me, did you get mine? I have no idea. It's anonymous. I can't tell. Okay. I did, leave open the option that some of you might think that it's not actually anonymous, but it is in fact anonymous. And if it's not anonymous, I don't know how to not make it anonymous. I wouldn't do that to you, even if I knew how to do it. So anyway, so today we're going to talk about viscosity and shear. And I love this stuff. I think it's really, really, really cool. So let's see, I'm going to show y'all something real quick because this video is a little bit, oh wait, you guys are not sharing my screen. Let's go Zoom. Stop share. So today I'm going to show you a few more YouTube videos again. So some of you guys are probably aware that, I did grad school in California. So I think California is like really beautiful. In fact, I think it's probably pretty hard to argue that. But I want to show you just something to think about before we get into it. This is just kind of a really cool phenomenon that happens in Yosemite. So this is something called frazzle ice.
When we started Carvana, they told us that selling cars 100% online wouldn't work. But we went.
We're on Yosemite Creek below Lower Yosemite Falls. It's a cold, early April morning, and we're watching the frazzle ice formation. Frazzle ice are these small crystals of frozen mist that forms in Upper Yosemite Falls and Lower Yosemite Falls. The particles of ice wash down the stream with the liquid water in a slurry, a slushy, slurpy, goopy mass that in many cases flows like lava.
So if you can imagine in your mind a giant Slurpee machine that is putting out millions of gallons of Slurpee into Yosemite Creek, it's amazing. It's not snow, it's not ice, it's something in the middle, and to watch it move underneath a Yosemite Creek bridge is pretty incredible.
This is one of the more unique phenomena that you'll see in Yosemite if you're lucky enough to be here in March and April, which is the prime season for this. But it's an amazing thing to watch something this dynamic in Yosemite Creek. You see something that the millions of visitors who come in the summertime never imagined something like this.
It behaves a little bit like cement in some ways, that it stops and it forms kind of a stationary piece, and then the flowing pieces go past that stationary piece.
The ice will surge into place, and with enough thickness, it stops, and the creek will flow a different direction. The water will drain out of where it's just deposited it, leaving this what looks like snow, but again, it's soft, it's unconsolidated. You would plunge right into that. Now we see this dynamic change as the frazzle ice has built up its own levee and caused the channel to clog up, and it's coming toward us. We're gonna have to be ready to move here as the Yosemite Creek and all of its might is coming toward us. But you'll see this lava flow effect where the ice is going to accumulate and build up blockages that stop it from coming in a certain direction.
All right, this last little bit, and then we'll.
It's the full force of Yosemite Creek, which can be up to, say, 100 cubic feet per second. When that is.
All right, anyway, frazzle ice. Okay, so frazzle ice, to me, it gets me started thinking about, basically the resistance of a fluid to flow. Okay, and you can see with that weird ice, like it just kind of goes in a direction and it just says, yeah, we're not going to flow that direction anymore. And that's not necessarily a viscosity question, but it's just interesting. I don't actually understand what's going on there, but I just think it's cool. So we're going to share a white screen here. And what we're going to do is we're going to start talking about viscosity. And let's see. Okay. So we have some objectives today, some purposes. We're done with the fluid properties, which to me is, well, we're not completely done with them. We're just going to do this one last one. So the objectives of this lecture, basically, we're going to finish the fluid properties. Okay. And we're going to start here by we're going to define absolute or sometimes called the dynamic viscosity. And then we're also going to do and the kinematic viscosity. Okay, these are different things. They drive at the same thing, but the kinematic is easier to work with. But the absolute or the dynamic viscosity is, I think more fundamental. And then 2, we're going to apply Newton's law of viscosity. Newton's law of viscosity. Seems like Newton has a law for everything. And then 3, we're going to classify fluids. based on their viscosity. Okay, so this is like, well, my handwriting is really terrible. I think I blame this eye thing. Okay, so we're going to start with viscosity. So there'll be a few words at the beginning of this one. I've got, usually this is my favorite day of class because I bring in some stuff and we make some oobleck. I'm going to tell you guys how to make oobleck, and then I'll show you some cool videos on it. So it is a measure of a fluid's resistance to flow. Okay, and so what I want to say here right now, just because like a lot of people, they get pretty far into this class, and I guess, and they don't realize this, and I think this is maybe, well, it's almost certainly my fault, but so this is the symbol of the absolute viscosity. Okay, and we draw that like this. So again, if we're in, if we're learning how to do our writings, it's like this. It's like a U with a long tail. Okay, so U for, say, honey, excuse me, mu for honey. And yeah, I guess we pronounce that mu. Okay, mu for honey is much, much greater than mu for water. Okay, so that's the idea that I need you to understand. These thicker kind of like these things that would be very hard to stir, the mu for peanut butter is much, much greater than it is for water. The mu for air is much, much less than it is for water. Okay, so just that sort of thing. Okay, so now we need to think about like, what is causing this? Okay, so we're going to break down we're not breaking down the continuum assumption. We're going to think about like, why is there, why does it exist? Okay, exists, why does a fluid resist flow? It exists for two reasons. Okay, because 1 and 2. Okay, the first reason, okay, well, I guess both of these fall under the same thing, because of internal friction. Okay, whatever that is. Okay, that happens for two reasons, 1 and 2. Okay, and I'll describe both of them in a second. Okay, so 1 is molecular attraction. Okay, and I'll draw that picture in a second, or I'll do it right now. Okay, so when a fluid is flowing, we're talking about there's a shear on the fluid. Okay, so let's imagine you've kind of got a lake or something, or whatever it might be. Okay, and there's a bed down here, and maybe there's some wind on the top. Okay, so because of that wind, oh no, don't want that. How do we go back? Okay, so because of this wind, then what happens is this little thin layer of fluid right here on the surface, right? It wants to move at the same speed and at the same velocity as the wind above it. And so there's another little layer right below it, this layer right here. Okay, and those two layers are going to be interacting with each other. So one thing that's going to happen is, so I'm gonna zoom in right here. Okay, one thing that will happen is that this top layer, okay, its particles are moving at this velocity, and they are attracted to the ones in this layer beneath it, right, which isn't moving quite as fast. And so what's happening is, you could think of it like there's a particle right here and it's moving at a certain velocity, and there's a particle right here and it's moving at a certain velocity, and they're attracted to each other. So the one that's moving faster, it's trying to pull on its buddy and make it speed up. Okay, and the one, the faster one, or excuse me, the slower one is pulling on its buddy, trying to make him slow down. Okay, so the net effect is like, if you were to try to just mix this thing, like suppose you were paddling and you put your paddle right in here in that top layer of water, just in the top layer. Okay, you don't just get to move the top layer, because the layer underneath it is trying to keep that top layer from moving, because those molecules are attracted to each other. Okay, so essentially it resists that flow. Okay, and that's because of the viscosity of the water. So if the molecules in the fluid are very, very, very attracted to each other, it's going to be very, very hard to move the fluid. It's going to be very hard to make it flow. Okay, hopefully that makes sense. Okay, the more interesting issue with fluids. Okay, and obviously you can imagine with this molecular attraction thing, that can certainly be a function of temperature, right? Because you can, like you've nuked your honey before, or you've heated up your honey and all of a sudden your honey is really easy to stir, right? The viscosity of the honey decreased when you heated it up. Okay, and we'll talk about that in a second. The other thing that can happen is molecular exchange. Molecular exchange. Okay, and I'm gonna use this little layer drawing again, but I'm gonna redo it. So in this case, you've got these two layers, and again, one layer is moving faster than the other. Okay, now one of the things that's going to kind of equalize their the velocity in the top layer versus the layer beneath it is the fact that, okay, if you've got a little molecule right here and it's moving along at the speed of that layer, and then you've got a little molecule here and it's moving along at the speed of its layer. Okay, so this one has a high velocity, this one has a lower velocity. So what's going to happen though is these molecules, like they move around all kinds of crazy different ways. So this higher velocity molecule, it, in one of its crazy movements, moves down a layer. Okay, the effect of that is to speed up this layer, speed up the layer down below, okay, because you're bringing higher momentum down into a lower momentum layer. Okay, by the same token, you know, we could have this lower velocity, it could exchange up into the higher velocity. And when it does that, that's going to have the effect of slowing down the top layer. Okay, so the net effect of just that molecular exchange is to cause this layer to slow down by this amount, and this one to speed up by some amount. Okay, so in essence, this one speeds up and this one slows down. Okay. So in other words, the momentum of the layers is exchanged. And so the momentum is exchanged either through molecular exchange or because the molecules are attracted to each other. Okay, any questions on that?
Aren't those two very closely related? I guess I'm just having a little bit of a hard time kind of understanding the difference between attraction and exchange.
Okay, so exchange, you've got a molecule in one layer that actually moves into another layer.
Yeah, yeah.
Okay, with the attraction, we simply have one that stays in its layer and one that stays in another layer, and they're just pulling on each other.
Okay, so, okay, yeah.
I mean, they're both definitely going on at the same time.
Yeah, I guess that's what my problem was, really, is.
Yeah.
Yeah. All right.
Go ahead. Go ahead. Oh, you're done?
Oh, yeah, I'm sorry. Yeah.
Okay, yeah, no problem. So what's interesting about these things is they're both going on at the same time, but in different fluids, one of these will be very important and one of them will not be. So for example, we haven't gotten there yet, but we will discuss turbulence. And we discuss turbulence, as you can imagine, just from its name, this exchange becomes really important, and molecular attraction, it stays the same importance. So usually what happens is in that case, the molecular attraction, we say it's not important because the exchange gets to be so wild and so just so large by comparison that we don't even worry about the attraction. So for example, while I'm here, we'll go ahead and talk about it. So let's, I'll add this last little bit right here, is that we say like, okay, so for a liquid, for example, and this has to do with temperature, okay? So the viscosity of a liquid, okay, is a function of a temperature, just like in a gas. Okay, and So what happens as the temperature goes up in a liquid? As the temperature goes up, the viscosity goes down, okay? And you can think about your honey that way, right? Like, you know, you heat up your honey and all of a sudden you can pour it out of your thing. Before that, I think there's a lot of different things going on in honey, besides just that. But, you know, the viscosity decreases as the temperature goes up. And the reason for that is because the molecular attraction, so these cohesive forces decrease. Okay. And that's because, like in a liquid where the molecules are pretty close together, the cohesive forces are the most important thing, right? That's kind of what's driving your viscosity in the liquid. Okay, on a gas, what's interesting is that as you heat it up, the viscosity increases. Okay. And that's because, as you can imagine, in a gas where the molecules are so far apart and there's so few and far between, the cohesion between the molecules doesn't really even matter. Like, it's so small because they're not even really near each other. However, the exchange between different layers is huge. Okay. And if you heat this thing up, there's going to be more exchange because the molecules are moving around faster. Okay. And so that's going to cause the viscosity to increase. So that's going to be because the exchange increases. Exchange goes up. Okay, let me know if that makes sense to you guys before I move on. Okay, the most important thing to me that you understand here is this, that there are these two different ways that this thing happens, and conceptually what's going on. You know, this is less important because usually if you want the viscosity of a gas, usually get it off of a chart. And if you want it of a liquid, usually you get it off of a chart as well. However, getting numbers off of a chart is not really much thinking, right? It's kind of like, huh. And hopefully, like, whenever you look at charts, because depending on what kind of engineering you do, you will look at charts from time to time, look up numbers. Hopefully you're the type of engineer that when you get there, you go, huh, why does that line have that shape? Instead of just being like, I mean, obviously sometimes you've got a deadline or something, you just need a number. But hopefully when you have time to think about it, you'll say, you know, why do these things look the way that they do? Anyway, because, you know, that's what this is all about, right? Can you think your way through, you know, through things? Okay, so let's step away from that and let's start talking mathematically about absolute or dynamic viscosity. Okay, and let's see here. Okay, come on. Get out of here. I'll leave those objectives up there as long as I can. You know, I always find it really interesting. I've taught, you know, so many times, and I know there's so many students that really like having the objectives. And what I find really interesting is, like, when I was a student, I didn't care at all. But, you know, if I can help as many students as possible, that's, you know, everybody's just so different. Anyway, so absolute viscosity. So absolute viscosity has this symbol, mu. Okay, that's, I'm going to put in parentheses, absolute. Okay, and then there's kinematic, which looks like this. It's so again, if we do our little thing like this, okay, it's like a V that's kind of been bent out of shape. Where's my face? My face disappeared down here. Oh well. All right. So anyway, so this is called the kinematic. Okay, the relationship between these two is just a mathematical equation. So the relationship between these two looks like this: mu equals rho times nu. Okay. Oh, this is pronounced nu. Okay. You know, I wish I had a good, you know, you know, Rocky says, "Can I have a treat?" I say, "No." Anyway, so this relationship basically is just comes out because in the math, they noticed as they were working problems, they constantly were ending up with mu on rho inside. Like, they're like, you know, you're doing all this complicated math and you're constantly having to write mu on rho. And so they were like tired of that. And so one day they said, okay, let's just create a new quantity called the kinematic viscosity. And the kinematic viscosity is easier to work with usually. The reason for that is because the absolute viscosity has units of, or has mass times length over time. Okay, and kinematic viscosity has units of length squared per time. So the kinematic viscosity is just easier to work with. All right, however, the absolute one is probably the most fundamental. Okay, so we're going to talk real quick about, let's see, something with this that's called Couette flow. Okay, and you don't need to know about Couette flow. You know, if you just were a grad class, you know, it would be like the classic Couette flow problem. But here's the Couette flow problem, and we're talking about absolute. Kinematic is like a mathematical construct, but you can often look this up in a chart. But for this class, we're really going to be focused, or for this particular class period, we're really interested in this absolute thing. And so Couette flow is flow between plates that looks like this. So you've got a plate, and then you've got a, you know, some kind of surface, or it could be just another plate, and they're separated by some distance. And this top plate is being pulled over a fluid that's between the two plates at a velocity, I'm just going to call it capital V. Okay. And so what's happening is between those two plates, if you give it enough time, what's going to happen is we're going to get what we call a velocity profile. And the velocity profile is basically a picture of the velocity between the two plates. So maybe if I did, if I say this is my X direction, this is my Y direction, then I can say, I don't know, let's give this a variable. Let's say they're H across. Okay, and so what's going to happen is the fluid at the top is going to be dragged along by this top plate at a velocity of V, and the fluid at the bottom is not going to be able to move because it's being held in place by the bottom plate. And so we're going to get a flow that looks like this. Okay, if this is at a steady state, so it's been given enough time to come to you know, equilibrium. So this is the velocity profile. U, lowercase u, means velocity in the X direction. It's a function of Y. Oh, it looks like it's about to start storming out there. All right, so this is kind of what happens. Hold on, I need some light in my room. All right, so there you go. So there's, you know, the velocity profile. So when, I can't remember if you actually draw any of these in this class, but there's two rules for the velocity profile. So the velocity profile, there's two things that are going on here, the velocity profile. Okay, and one, okay, flow cannot be perpendicular to the boundary. Okay, which means that basically at this point right here, okay, the flow cannot have a vertical component. Okay, it also can't have a vertical component right here, although it has no components right there. Okay, and the reason for that is because if it did, then that would mean that some of the fluid was going into or out of that solid object, which is impossible. Okay, the other thing that we say is we have what's called a no slip condition, which basically says the velocity at the boundary has to equal the velocity of the boundary. Okay, so from that, what we're going to get is we're going to get Newton's law of viscosity, which maybe we'll put it right here. And it looks like this. Okay, Newton's law of viscosity is that the shear stress equals mu, in this case, du dy. Okay, and this is kind of an interesting statement. And so what I want you to do before you just like write that down and go, okay, what? Or you're thinking like, what is the tau? What's going on here? Okay, this is the shear stress. This is the velocity profile. This is sometimes just called the shear. I will call it both, velocity profile. And this is the absolute viscosity, absolute viscosity. Okay, if you want to know, like, what are the units here? Like, if you're ever like, what are the units of mu again? I can't remember the units for the absolute or the dynamic viscosity. Well, we can figure it out from this. So this shear stress, this is like, let's see, it's a stress. So it's newtons per meter squared. Okay, that equals, well, I don't remember what this units are. U has meters per second, and dy has units of meters. Okay, so let's see here. So that means if I rearrange this, I'm going to get 1 over seconds equals newtons per meter squared. Okay, and if I rearrange this, I'm going to say, well, this really should be square brackets to say units, because that's what we're doing right now. So I'm going to get newtons times seconds per meter squared equals the units of viscosity. Okay. Now you're kind of like, well, that's not what you just said. You just said mass something, 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 something. Okay, so to do that, what we do is we remember force equals mass times acceleration. And we take this newtons and we change it into mass, kilograms times acceleration, like that. And then if we rearrange that, let's see here, we end up with a seconds on the bottom, a meters on the bottom. Come on, give me that meters. Meters on the bottom times second on the bottom and kilograms on top. That equals mu. Okay, so mu is mass over length over time. Wait, I must have made a mistake. Did I make a mistake here? Yes, it did. No, did I? Seconds, newtons times seconds per meter squared. It's frustrating. Doesn't seem like I made an error. Let me get back to you on this. This seems correct right here. This seems correct. So I think earlier when I said it was mass times length per time, I'm not seeing that. Let me check on that later. Okay, I'll get back to you guys. But anyway, this is how you just play with units to make sure that things work. Okay, the last thing, I'm not as concerned with this. Okay, I am very concerned, although I am concerned that you guys know how to get units or figure out units if you make a mistake, things like that. But what I want to do is I want to think about, what does this mean? Okay, what does this mean? Okay, and I want you to think about it in terms of force equals mass times acceleration. Okay, meaning this is what's driving something to accelerate. This is the response. Okay, this is the resistance to that response. Okay, if you have something really, really, really big and you apply a force to it, you're not going to get much acceleration. If you have something really, really small with that same force, you're going to get a lot of acceleration. So I want you to think about this in the same way, okay? Shear stress is creating this velocity profile, okay? It's causing there to be a difference in the velocity between two layers of the fluid, okay? And this viscosity is what's resisting that. Okay, so if I go over here and I'm like, okay, let's look at these, let's look at two layers. Okay, so I'm gonna look at this layer right here and this layer right here. Okay, between these two layers. So I'm gonna look at those two layers. So let's see, let me draw the layers. Oh, come here. Come on, you can do it. So here's one layer. Here's the layer underneath it. Okay, the layers. So basically there's a stress, there's something pulling, on this top thing right here. Okay, there's a stress right here. Okay, there's a force acting on the top of that layer. or really, I guess it's technically it's between these two layers, but you know, this is all, you know, infinitesimally small. And what that's causing this to be is it's causing there to be a difference in velocity, delta U, between these two layers, delta Y. Okay. And the viscosity is trying to prevent that. That's the resistance, right? So what's happening is either these particles are pulling on each other or they're exchanging with each other. Okay, but basically it's trying to prevent, it's trying to make du dy equals 0 by, you know, by those things like pulling on each other. Okay, instead, however, we're applying a stress, tau, on the top. Okay, there's another way to look at it. Sometimes you can look at a system and you could say, well, if I've got a velocity profile here, then I can infer that there's a stress in the fluid. Okay, and you could do that with the same thing with a ball. You could say this ball is accelerating at 9.81 meters per second squared. So I can infer that there's a force on that ball that's causing it to accelerate. Okay. So anyway, questions about this? Because I know that this is, you know, there's a little bit of calculus in here. Questions? Are you guys still there?
I'm a little lost, but I guess maybe a sample problem may clear up some stuff.
Okay, well, talk to me about what you're lost on, because I want to keep this conceptual for a second.
Well, I guess I don't really have much to relate it to right now, so
Okay.
I'm just trying to. I guess when you put it to use, maybe it'll make more sense.
I guess what I'm trying to avoid is I don't want us to just be able to get the answer and not kind of understand what's going on here. But let me.
I understand the formula.
Oh, well, right. That's what I'm saying. But what I want you to understand is what the stress is doing. So the stress is a force, and it's spread out over this area right here. And what that's doing is that's pulling on this top layer of the fluid right here. Okay, which is pulling on the layer just underneath it. Okay, so there's a stress between those two as they slide over each other. Okay, so let's I'm going to give you another velocity profile and we'll talk about it there. Okay, so let's see. Okay, we'll keep that velocity profile. Do this. Okay, we're going to keep our rules for velocity profiles. This is 1 and this is 2. Okay, and then we're going to do another one. So these rules apply to this one. We're going to add 2 more rules so those 2 rules only apply to the last one. For this one, we're going to create something else. Okay, so this is like flow in a pipe. So you've got a pipe and it's moving sewage or drinking water underneath the streets of the city of New Orleans. In this case, it's going to be drinking water because this one's all the way full. The ones that bring sewage water are usually not full. Okay, and there's a good reason for that. Okay, so what happens in this case is we have the same rule, this no slip condition, which means the fluid is moving through this pipe because it's pressurized. So we've got high pressure over here, and we've got low pressure over here. Okay, and so because of that, we're going to get a velocity profile where it can't move on the edges of the walls because there's too much friction over there. Okay, the no slip condition means that the fluid can't move there. But in the middle, somewhere in here, it's going to move pretty quickly. And so it actually, if you do the math on this, well, if you do the math, it depends on whether or not it's laminar or turbulent. If you were to assume it's laminar, which it isn't, you would get a nice parabola. Okay, and you would get this flow that looks like this. Okay, so what we would want to know in this case is we would want to sit here and we would say to ourselves, okay, where is there stress in this fluid? Okay, where is the shear stress in this fluid? Okay, and so what we have to do is we have to think about the stress being between 2 layers. Okay, so for example, if I'm going to define some layers here. And so let's suppose where layer is like right here, and the next layer right next to it is like right here. Okay, so the stress between those two things, if I were like, okay, I would go up here and I would say, okay, well, tau, the stress between those two layers equals U, and I'm going to make it approximately equal, but it's going to be this stress in this top layer, and this velocity in the top layer, U top minus U bottom. Okay, that's my du, and now my dy is just the distance between those two layers. Okay, the y at the top minus the y at the bottom, the y at the top minus the y at the bottom. Okay, and that goes for any layers in this whole thing. So I could do that here if I wanted to, compare the stress between those two layers, et cetera, et cetera, et cetera. So then the question becomes, in this case, is where is the stress the highest? I'll give you all a second to think about that. Where is the stress in this fluid the highest?
Is it near the edges?
It's near the edges. Now, why is it highest near the edges?
Because it has the most resistance right there.
Right. So there's the most friction right there. Absolutely. But like, why mathematically based on this formula here?
The curve is the sharpest.
Yes, it's the steepest, right?
Yes.
The velocity at the top and the bottom of any infinitesimal thing is very, very, very steep. So like right in here, if I were to draw it kind of as a straight line, you can imagine this is very steep right here. Okay, du, dy is very large right there. Okay, so in this case, 3, okay, the stress, or tau, is highest near the boundaries. Boundaries. Okay. Now where's the lowest?
At the top of the curve?
At the top of the curve. Okay, if we look right here, okay, notice that there is no du dy. Okay, so for it's the lowest in the center. Stress is lowest in the center. Okay, and that's because there is no du dy. This number right here is 0. Okay, the other way to think about it is if I were to look at these two layers right next to each other, like here's a layer, here's the layer next to it, right next to it. Okay, so if I draw these two layers, okay, now I've got a molecule in each one, this molecule and that molecule. How much stress is there between them when they're like holding each other's hands, right? Is that stressful for them? No, they're pretty happy. They're like, they're skipping into the field singing songs. And they're like, you're both going the same speed. This is great. There's no stress between the two of them. They're just holding hands. Okay. On the other hand, if a molecule is here and a molecule is here, and they decide to, switch sides, it doesn't matter. Like one goes up, one goes down. It is not changing the momentum of either side, of either layer. Okay. And that's what happens when the du dy is 0. Okay, there is no change in velocity with a change in height right there, right at the middle. Okay, and so as you can see, this slope here, okay, that changes as you move in this direction. So the slope gradually gets steeper and steeper until it's right at the steepest, right at the edge there. Okay, any questions on that?
What type of questions could you ask in a problem like this besides the stress on the boundaries?
Besides the stress on a boundary, I don't know. I mean, I'll give you some example problems in a second, but I could ask what's the stress in the middle, and you would the easy answer would be 0. I could ask you the stress pretty much anywhere, but I'd have to give you some numbers to work with. So yeah, so let's do a quote unquote example problem. But before I go into example problem, anybody have any questions about this? Okay, because what we're doing is essentially we're gonna apply Newton's law of viscosity. Okay, let me do this real quick. Let me close these. You need to go away. You need to go. Okay, let's see what we can do here. All right, so I'm gonna delete a lot of this. I'm gonna leave this law up I'll leave the word shear stress and all this other business here. Okay. Okay, so I'm gonna do that. This is a Couette flow problem. Come on. Now this will take me a little longer than it should because I have to write this out. Normally this would be on my PowerPoint. Come on, buddy. Okay, I can't delete that bottom right corner because my stupid camera is putting my face right there. Okay, let's see what we got here. Come on. Okay, it won't do it. All right. So here's the problem. This is an example. Okay, glycerin at 20 degrees F is used as a lubricant. Get used to that in this class. We like to use lots of different random fluids to force you to look stuff up in a chart between a stationary surface and a moving plate Okay, that has an area of 2 square feet. The glycerin, or the gap, is 1/4 inch thick, and the plate is moving at V, capital V, equals 5 feet per second. Find tau and F shear. Okay, so what we have to do here is we have to make an assumption. Actually, the assumption was written into my problem, but I'm going to make an assumption real quick. Okay. Well, I'm going to show you why I make this assumption. Okay, so first I'm going to draw a picture. I find that students don't like to draw pictures. This is a mistake. I don't know why y'all don't like to draw pictures, but when I was a student, I didn't like to draw pictures either. But like if ever you have to do an oral exam where like, you're standing up in front of professors and they start asking you a question, the best thing you can do to delay and to think is to draw a picture. It helps you think, it helps you visualize, but it also buys you time. Okay, so all right, so a lubricant between a stationary surface and a moving plate. Okay, so here's a stationary surface. Here's a moving plate. Okay, the moving plate, we've got this 2 square feet. Okay, that 2 square feet, that's an area. Okay, we have to think about what that means, and that is this area right here, 2 feet squared. Okay, this is glycerin between these two because it's being used as a what do you call it? Lubricant. It's a 1/4 inch thick, 1/4 of an inch thick, and the plate is moving at V equals 5 feet per second. 5 feet per second. Okay, find tau and F shear. So a problem here is I don't have the velocity profile. And so this is where we're going to make an assumption. So this is just a diagram. So this is given. Oh, here's required. And now we're going to do our solution. And so what we're going to do is I'm going to make an assumption, and I'm going to show you what that assumption is in a second. So right when that plate starts moving, the velocity profile looks like this. And then the plate starts moving. And what's going to happen is, right, it's going to start to pull that fluid forward. Okay, and it's going to start pulling that fluid forward and forward and forward and forward until like each second later, more and more of the fluid is going to be pulled forward, because you know that information doesn't travel instantly down to the bed. It's going to take some time until we get here. Okay, until it has like completely and totally reached the bed. Okay, and once it's done that, okay, so the assumption that I'm going to make is that du d z or dy is constant. Okay, and what that assumes is it assumes we've had time for this fluid to get to that point. Okay, where you know like that this is a steady state system. So what we're going to do is we're going to go ahead and solve this problem. And what we'll say is we'll say, okay, well, I want tau. So I'm going to say, well, tau equals du d. Oh, sorry, I forgot my my mu. Mu times du dy. Okay, and if this is constant and mu is constant, then tau is constant everywhere. Same stress on every layer of this fluid. Okay. The other nice thing here is du dy, I can get at that pretty easy because this is a line. So du dy is just the slope of a line. Okay, so we can go ahead and start solving this. So tau equals, now mu, we have to look up in a chart. Okay, so you have a chart in your book and that's where you'll go and you'll look this up. I actually haven't written down where the chart is in your book. But this mu, we just look up in a chart. So this is going to be 2.95 times 10 to the minus 2, and this is going to be pounds times seconds per foot squared. Okay, and now we need to get the du dy. Okay. I just need the slope of that line. Okay, so the slope of that line, the change in u, because it's the line, so the change in u, well, we're going to go from u equals 0 to u equals 5 feet per second. So I'm going to say, I'll go ahead and like write this out, even though it's a little bit trivial in this case, 5 feet per second minus 0 feet per second. Okay, those are 2 points on the line. And then I'm going to divide that by the y's, so dy on the bottom. So the y on the bottom, well, we didn't even define a direction, but let's make this y here. So the y on the bottom is 0 inches. Let's not make it inches. We don't want to work in inches. 0 feet minus 0 feet. And on the top, we've got 0.25 inches. So I'm going to divide that by 12 to get me feet. Okay, it's kind of annoying, right? But that'll give us an answer. So tau equals, let's go ahead and do the little math here. Actually, you know what? I've already got this worked out. But I don't have it worked out the way I like it. So 2.95 times 5. See, I guess we'll divide, but we'll multiply times 12. And then we'll multiply times 4. All right. No, we'll divide by it. Sorry. Okay, something's wrong here. Doing something wrong. All right, we'll do 5 divided by 0.25 over 12. 240 times 2.95. Oh, I forgot my I forgot my times 10 to the negative 2. Okay, so we get 7.08. And then we look at our units. Always important to make sure units work. So this becomes per second because the feet per second cancels with the feet and I get 1 over seconds. So that cancels with the seconds. And I'm left with pounds per square foot, PSF. Okay. And then I want the force. Okay, so basically this force is asking, well, how much force do I have to put on this to make this happen? Okay, well, force equals tau times area. Okay, and you have to think the area over which that force is being applied. Okay, and this is a shear stress. So the force is a shear. So it's going over this area right here. So a common error that my students make, if I give them lots of different areas, like I might give you the area of the front here, I might give you the area of the bottom. Okay, this is a shear stress. Okay, so it is shearing. This area on the front or the back does not matter. For a shear, it is only because the force is right here. So it is only this area. Okay, that's where the fluid is like you can imagine, the bigger this area is, the more fluid is pulling back on this plate. Okay, so we're going to multiply this times that area. So F equals 7.08 pounds per square foot. We're going to multiply by 2 square feet, and that's 14.16 pounds. Okay, and I'm going to give that to you in a single solitary number, which is 14.1 pounds. Okay, keep 5. There only happened to be 4 on this one, but keep 5 and round to 3 when you report. Nope, 14.2. My apologies. Okay, questions? Dominic, does that answer your question about how we might solve a problem?
Yeah, that was perfect.
Okay, now in the homework, it's going to get more interesting because they're just going to have different areas and things that you have to work with. Because what I want to make sure is that you can figure out, you know, which area you're working with. So like in this one, I want to make sure that you know that we're working on this area right here. Okay. Other problems, I'll give you another example, and then we're going to go quickly into classifying fluids. We don't have a lot of time, which inevitably happens on this lecture, which is weird because I always think this is going to be a quick lecture. Come on, race. I don't have all day. Come on. All right. Erase, 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 erase. Must be a bigger eraser. I know there are better whiteboard programs than Zoom. All right, so another problem might be instead, if you look at my PowerPoint, I've got this one already like created, but it's like, okay, so we've got flow in a pipe. Okay, it's being driven. Usually, this is pressure driven flow usually. And we've got a profile that looks like this. Okay, you can imagine that this is a more difficult problem. Okay, so this is my X direction. This is my Y direction. Okay, and I'm given this, and I'm also given that Y in millimeters, and the velocity should be U in meters per second. Okay, I'm given this chart. This is 1 millimeter, 2 millimeters, 3 millimeters away from the wall. Okay, or up, I guess. So it's 1 meter per second here. It's 1.99 meter per second, another millimeter up. And at 3 millimeters up, it's 2.97 meters per second. And then it says, and then last thing, it gives you the viscosity. Mu equals 10 to the minus third newtons times seconds per meter squared. So then required, and I'm going to be a little bit out of order here, but the required is tau max equals what? And tau min equals what? Okay. So the way we solve this, okay, well, we're looking for tau. Okay, the formula for tau is right here. Mu du dy. Okay, tau max is where this thing is steepest. Okay, that's happening at either one of the barriers. Okay, we can't quite get at what's happening right at the barrier, but we can get pretty close. Okay, I can create another line on this chart that I know that at 0, millimeters, that the velocity is 0. So for max, I'm going to go as close to the wall as I can. So we'll say tau max equals this viscosity, 10 to the minus third newtons times seconds per meter squared. Okay, and now I'm going to get at du over dy. I can't get that exact, but I can get it approximate. And this is the best you can do with this problem. Okay, so I'm gonna get as close to the bed as possible. So I'm gonna go from a Y value of 1 millimeter, except I don't want millimeters, do I? I want meters. 10 to the minus 3 meters, minus 0 meters. Okay, so that's as close to the bed as I can get using this point and this point. And then I'm going to use 1 meter per second, that's the U, minus 0 meters per second at the bed. Okay. And again, if we check the units here, this becomes meters per second over meters right here. So this becomes 1 over seconds. So that's going to cancel with this seconds right here, and I'm going to get a pressure. So tau max equals, if I plug that in, a very boring plug-in, because you can see that this cancels with that basically, and I'm left with 1 Newton per meter second squared, or 1 Pascal. Okay, and what's T min? Somebody shout it out.
Where the slope is like the flattest.
It's the flattest. So what's where it's flat, what's the velocity profile? Oop, didn't mean to erase it. Anybody? What's du dy right there?
0.
0.
0. So the minimum velocity, this is a trivial question, okay, in this problem, right? It's not necessarily going to be 0 if the velocity profile doesn't flatten, but if it flattens, you just say it's 0. Okay. Questions? Okay, last thing that I'm going to do here, and this is the bit where we're going to classify fluids. We're getting some lightning over here, or thunder. All right. And hopefully I might be able to, hopefully I can borrow you guys for like 2 extra minutes. If you have to leave, can you come back and just watch this after I record it? I'm going to show you like one of my favorite things in this whole class. Okay, so lots of fluids get classified, and this doesn't matter for this class. It's never going to show up. But here is a fluid. So this is the strain rate. Okay, it's also called the strain rate, or the velocity profile. And this is the stress in the fluid. Okay, almost all fluids that we're going to work in this class use this equation right here, tau equals mu du dy. And that is, so basically, this is so if you were to plot this over here, so you think y equals mx, right? So this is your y-axis, this is your x-axis, this is the slope, okay? So for most fluids, follow this law. This is Newton's law of viscosity. So it looks like this, and the slope is the viscosity. And this is what we call a Newtonian fluid. Newtonian fluid. Okay. There are other fluids, however, and I was going to talk to you guys about this a little bit, but we're kind of low on time. Here's my toothpaste, which you guys can't see, or maybe you can see. I can't tell if you can see my face or not. But you'll note that you would probably consider toothpaste to be a fluid, and yet look at this. I can like put it straight over my eye and point it straight down, and it doesn't go into my eye. Okay, so clearly it's got some stress on it, but it's not flowing. Okay, and so toothpaste, I mean, I guess it depends, but you would consider it, I would consider it something where it's got some stress, and until the stress gets above a certain level, until I squeeze it, it doesn't move. Okay, so all of a sudden we'll get to some point, and then it will start to flow. Okay, and so that would be, this is called a Bingham plastic. I can never remember this word, but I really like it. Bingham plastic. Okay, do not memorize this chart. You don't need to. Okay, it's just ideas in case you go other directions with. So an example of this would be toothpaste. Okay, and I don't think that toothpaste has the same viscosity as, say, water. Like if an example here is water. Okay, I don't know what the slope of the line would be for toothpaste. This is just conceptual. Okay, other ideas, there are some things that are what we call shear thinning. Okay, meaning the more shear you apply, the lower the viscosity. So at a low shear, we've got a lot of viscosity. Okay, so the line is steep. And then as you add more stress, okay, it thins. Can anybody think of something that's like this? As you stress it, it thins. Okay, this is called shear thinning.
Like Play-Doh?
Maybe that I'd have to think about that, but that might. Okay. But here's two things that come up: blood. Okay, like you know, when the blood is moving through your body, it's basically like water. All of a sudden, you get cut, and like if you spread it on your arm, it just it stops moving. Okay, there's a lot of chemical processes going on in there that make that happen. Chemical and biological processes. Another one, wall paint. Okay, and I think some of you guys can imagine this, like when you stir it, it's almost like water. Okay, so you know you're up here and you've got a very, very low viscosity. As soon as you stop stirring it, it just it thickens up. Okay, as soon as you stop stirring it, you know your stress goes down, and so you end up in a very high viscosity setting. And then the last one of the last possibilities here that almost never shows up is shear thickening. So this is something that the more you stir it, the thicker it gets. This is very rare. So the best example that I could think of for this is something called oobleck. And you can make oobleck at home. I'm 2 minutes over, so I apologize for this, but oobleck is like one of the coolest things. You do cornstarch and water at a ratio of about 1.5 to 2 parts of cornstarch to water. And I usually make this in class. And what it is like you can pick it up and you can punch it. And as long as you are applying a lot of stress, it behaves like a solid. Like it almost becomes a solid where it gets so steep that it's almost a solid. As soon as you stop stressing it, it turns back into a liquid. And I'll show you my last video here, and you can watch it on your own if you don't have time to here, wait, if you don't have time to be here, but trust me, this video is definitely worth it. Let me stop this share. I'm going to share screen, start broadcast. Come on, start broadcast. Okay, hopefully you guys can see what I'm doing. Let's go to here. And these guys create by the way, I once had a date where we made oobleck on our front porch. We ended up dating for a year, so it was pretty cool.
I know a thing or two about cars.
It's like our first date.
Sometimes buying them can make you tighten the chest.
But these guys have a ton of oobleck.
Déjame, ya estoy acá. Una. No. Necesito silencio, que si no ya tengo yo bastante miedo, ¿no?
So if they hit it hard enough, it's going to behave like a solid.
Déjame.
So as long as the shear is high enough, it will support their weight. If they put their foot down there, it's too soft, it's going to behave like a liquid and they're going to sink in. And one day I'd love to do this. You can look at college campuses all over that have gone through trouble. It's just cornstarch and water. It's really easy to make. Google oobleck, you will see elementary school teachers kind of, teaching their kids how to make slime. Because it feels really weird. So I recommend stir some up, go get some cornstarch, mix it with some water, and just kind of punch it, feel it, try to stir it. The other problem is the longer you have it,
Llegamos a quedar en el centro, nos hubiéramos hundido,
kind of weird things going on inside of it, so it takes a little bit of time.
Me voy a quedar en el
I think
centro
he's going
para
to
que
fall
vean que
under
no hay
it this
truco.
time. I think think this would be the same idea as like quicksand. You know, we always had this idea growing up that there's quicksand, that the more you struggle, the more you couldn't get out. And I would think that this stuff would work out. Anyway, that's all I got for today. If you have time, look at the rest of it. But I'll go have a good day, and I'll see you all next time. If you have any questions, just hang out.
Aquí, vení. Se puede hacer descansar.
And I can talk to you guys about how to make that stuff. It's fun. It does make for a good date as well. So any questions, hang out. I'll be here.
Thank you.
Thanks, guys. Have a nice weekend.
You too.
Sorry, I went over.
Bye, thanks.
Sorry, I went over a little bit. That's a little rude. Looks like most of you guys stayed, so that was nice of you. I'll try to be a little bit more time conscious.
Excuse me.
Yes, sir.
On the Connect homework,
Yep.
you know, there was a question on the vapor pressure.
Sure.
I got it wrong because I capitalized the P in pressure. Is there any way you
Yeah.
can fix that,
If you
or
can-
just not
if you can try-
capitalize the P?
If you can fix that, just because it should take, because you only have to fix that one problem. You don't have to redo the whole assignment, I don't think. If you can fix it, if not, send me an email and just remind me, because like I'll post your grades at some point, and if I forget, I mean I won't remember, but just send me an email then and be like, hey, remember you said that on problem whatever, and I'll go in there and I'll fix it. It's no problem.
All right, thank you.
Yeah, no problem. All right, you're welcome.
Have a good day.
You too. These exercises. Where is my, it's time to stop recording, stop share. Stop recording. Okay. We still recording? Stop recording.